A detector sensitive enough to feel a passing gravitational wave is also sensitive enough to invent one. So here is the method for telling the difference, the accuracy it actually reaches, and the place where it stops working. I am Molly, and this is Humanitarians AI. Today's method comes out of gravitational wave astronomy, and it is worth your time because the hard part here is not the physics. It is trusting the instrument. Here is the whole idea in one breath. A gravitational wave detector produces far more noise than signal. So scientists turned every glitch into a picture, had volunteers sort and name those pictures, and trained a neural network on the labels. Naming the noise is what makes a detection trustworthy. August 17th, 2017. LIGO records a real neutron star merger. 1.1 seconds before it, a converter saturates at Livingston and drops a glitch on top of the signal. The automated search cannot register both detectors together, so the first alert goes out on Hanford alone. That was not a rare accident. In LIGO first observing run, 51.5 days, the detectors logged about 1 million glitches. The team that characterizes the detector is small. Hand sorting was never going to scale, and some of the noise is actively deceptive. A blip is about 10 milliseconds long and spread across a wide band, and in a time-frequency picture it looks like the chirp of a massive black hole merger. Standard consistency checks cannot tell them apart. So here is the method, and it has 4 parts. Every glitch becomes a spectrogram, shown at 4 time windows at once. Volunteers sort those pictures into named shapes. A convolutional network trains on their labels. Then the network sorts the incoming flood first, and routes the cases it is unsure about back to people. Run 1 blip through it. 4 windows at once, so the fine structure and the context are both visible in the same view. Volunteers who have seen thousands of these call it a blip. The network, trained on those calls, labels the next one in milliseconds. The numbers. On held-out test data, the first classifier reached about 97% average accuracy across 20 named classes. By the end of the third observing run, it had labeled more than 600,000 glitches. Now the part that decides whether you should use this. A trained classifier can only name a shape it has already seen. In beta testing, volunteers found 2 morphologies the machine had no class for, nicknamed paired doves and helix. The people found them, not the network. Be precise about scope. This classifier does not detect gravitational waves. Matched filtering does that, and it is classical signal processing, not a trained model. It also did not clean the 2017 glitch. Bayes' wave did that one event. Naming a whole category of noise continuously is the job it is for. Let's recap with Claude. The problem is trust, not detection. The method is a picture of every glitch, human labels, and a network trained on them. The result is about 97% accuracy and over 600,000 glitches named. And the limit is the shape nobody has named yet. Your turn. Paste this one. I have a labeled dataset where 2 classes look nearly identical and one is rare. Walk me through the human in the loop step that catches a class my model has no label for, the metric that exposes the confusion between the 2 lookalikes, and the test that would prove the pipeline failed. Then grade the answer on 3 things. A named metric. A human where new classes appear. A stated failure condition. Knowing the noise by name. Humanitarians AI. I am Molly.